tetragonal crystals, there are two kinds of Bravais lattices I have seen, the simple tetragonal lattice and the body centered tetragonal lattice. The important point to note about tetragonal crystals is the presence of one and only one fourfold axis. Of course, it could be a proper fourfold axis or it could be a 4-bar kind of an axis, which is a roto-inversion axis. Now, if you write down all the point groups, you will notice that the 4 is in the first place in all these point groups. The lattices which have the highest symmetry, that means tetragonal lattices, always have the 4 by m, 2 by m, 2 by m symmetry, while crystals based on these lattices could have a lower symmetry, and those include the 4 bar 2m, the 4 mm, the 4 2 2, the 4 by m, 4 bar and 4 point groups. We have already seen that the preferred unit cell is described by these lattice parameters for the tetragonal crystals. The lower symmetry one compared to the tetragonal crystal is the orthorhombic crystals, wherein we see that there are all possible Bravais lattices for the orthorhombic case, the simple orthorhombic, the body centered orthorhombic, the face centered orthorhombic and the end centered orthorhombic lattice. So, we can make crystals starting with these kind of lattices, and the point groups which belong to this orthorhombic crystals are the ones listed below, the 222, the 2 mm, the 2 by m, 2 by m, 2 by m point groups. All orthorhombic lattices, any one of these 4 would always have the highest symmetry, which would be a 2 by m, 2 by m, 2 by m symmetry, while crystals based on these lattices could have a lower symmetry, which could be a 222 or a 2 mm symmetry. And we also seen that one convention which is typically used to describe the unit cell is wherein A is less than B is less than C, and we have already noticed that this is the interrelationship among the lattice parameters for the orthorhombic crystals. This is obviously for the preferred unit cell, and that means that you can obviously have alternate choice of unit cells as well. Hexagonal crystals, we have seen, are characterized by the presence of a 6-fold or a 6-bar axis. You can see a 6 here in the first place, and a 6 here, a 6 here, 6 here and so forth. So, all hexagonal crystals should have some form of a 6 in the first place in the point group. There is only one kind of lattice, as we have seen, which is the simple hexagonal lattice, and one of the important crystals, the hexagonal closed pack crystals, belong to the hexagonal crystal class, and we will try to understand that crystal in lot of detail in one of the coming lectures. We already seen the lattice parameters, that C is not equal to A, which is equal to B, and the alpha and beta are both 90 degrees and gamma is equal to 120 degrees. So, this is the preferred choice of unit cell for the hexagonal crystals. And as before, the hexagonal lattice always has the 6 by m, 2 by m, 2 by m symmetry, while crystals based on this lattice could have one of these lower symmetries, which includes a 6 bar m2, a 6 mm, a 622, a 6 by m, a 6 bar or a 6. In other words, there are quite a few point groups which belong to the hexagonal crystal class, and crystals belong having any one of these symmetries would come under the hexagonal crystals class. The important point to note is that unlike the 2-dimensional case, where the presence of a 6-fold or a 3-fold, a single 6-fold or 3-fold, both came under the 120 degree rhombus class, here the single 3-fold cases are excluded from the hexagonal class. They come under a separate class, which is the trigonal class. So, in trigonal crystals, and we had already seen how we can go from a unit cell of a cubic to a trigonal unit cell by pulling along the body diagonal, and if you do such an operation, we will end up with A is equal to B is equal to C, alpha, beta, gamma all equal but not equal to 90 degrees. That means these angles can be any general angle. In this case also, we have only one kind of a lattice, the simple rhombohedral lattice, and all rhombohedral crystals are characterized by a 3-fold or a 3-bar axis, of course, a 3 in the first position. We had noted earlier that cubic crystals, the way they are written, are characterized by 2 3-folds, and the 3 occurs in the second place in the point groups. In the case of trigonal crystals, and rhombohedral being a synonym of trigonal, we note that the 3 is in the first place. So, all rhombohedral lattices and some crystals based on them would have 3 bar 2 by m symmetry with the 3 in the first place, and rhombohedral crystals could have a lower symmetry, and these symmetries include 3m, 3-2, 3 bar and 3. So this is an important distinction to be noted. Whenever a point group is written and we note that the 3 is in the first place, then we have to be sure that it is a trigonal crystal, and whenever the 3 is in the second place, it refers to a cubic crystal and not a trigonal crystal. Additionally, in the trigonal crystals there is one and only one threefold axis, while in cubic crystals they at least have two threefold axes, which automatically results in four threefold axes. So that has to be kept in mind in differentiating the cubic crystals from the trigonal crystals. If you go down lower in symmetry, we have the monoclinic crystals, and we have already seen that the monoclinic crystals can be based on two kinds of monoclinic lattices, the simple monoclinic and the end-centered, which is sometimes called the base-centered monoclinic lattice. This centering could be the A or C centering. In other words, the centering could be opposite the A vector or opposite the C vector. So we could have two kinds of centering for the end-centered lattice, and therefore crystals based on these monoclinic crystals could have that centering, and the symmetry of monoclinic lattices is always at least has a symmetry of 2 by m, while crystals based on monoclinic lattice could have 2 by m, 2 bar or a 2 kind of a point group symmetry. We can clearly see that as we go down the list, the symmetry of the crystals is lowered, and we will soon classify them on a decreasing order of symmetry in one of the coming slides.
Yeah. The point group you have written, the order you have written is specific?
Okay. Mr. Ravi has an important question that I have written these point groups in a certain order, way. Okay. Is this any specific order to it? I don't remember the way in which I wrote the order, but the most specific way of the right way of writing is by increasing order of the point group. So each point group is defined by the number of identity point it leaves. In other words, how many of independent symmetry operations it has got, and if you count those number of symmetry operations, which would be called the order of the point group, the most preferred way of writing these point groups is by an increasing order of the point group. Okay, that's the way of writing it correctly.
Actually, as you have told that 3 is in the first position, so is there always 3 in the first position, or it can be?
Okay. Oh, we are asking two independent questions.
Yeah.
So Mr. Ravi's specific question is that regarding the position of the 3, and in this case the position of the 2 perhaps. We are answering two independent questions. Are these point groups in the way they are written, are they written in a particular sequence which is a logical sequence? So the point number 2 is, of course, within a to differentiate one kind of a crystal from the other. When you differentiate one kind of the crystal from the other, then we worry about the position of the 3 or the position of the 2 or the number of these kind of 2 by m. For instance, in orthorhombic crystals, we had seen that it has got 2 by m, 2 by m, 2 by m. In other words, all the primary axes are having 2 by m symmetry, a two-fold and a mirror perpendicular to it. But this monoclinic crystals have just one kind of such kind of 2 by m symmetry along one of the axes, which happens to be the preferred axis B typically. Now, further I am telling that the logical way of ordering these point groups, apart from the, of course, the highest symmetry one, which is the symmetry of the what we may call the holohedral class, is also to order it in terms of the increasing order of the point group, which I am not sure I have done here. So, and we had pointed out that the lowest symmetry one is a triclinic crystal, and a triclinic crystal, for instance, has no special symmetry. The highest symmetry you can think of is the center of inversion, which is a 1 bar kind of symmetry, and triclinic crystals are basically characterized by the translational symmetry, and of course if 1 bar is present, we also cite that kind of a symmetry. And we have noticed that for the triclinic crystal, they are always based on the triclinic, single simple triclinic lattice, and there is no special relationship among the lattice parameters for a triclinic crystal. So we have slowly gone through the 7 crystal systems. We have briefly outlined the symmetry and the preferred unit cell and the lattices which belong to this 7 crystal systems, and we have more importantly noted, when we especially discuss the cubic crystal, is the connection between the shape of the crystal and the internal symmetry present in the crystal. And this is what is written in the first sentence here. The external shape reflects the point group symmetry of the crystal, and this is a confluence of the mathematical concept of point groups and the practical concept of shape of crystals. And we have already noted that the unit cells can be chosen according to our need at the point of time, but there are always preferred unit cells which we conventionally choose. And we also notice that all kind of lattices may be present, or it may just be based on the primitive kind of a lattice. Okay. Next, we will try to order the 7 crystal systems, the ones we have considered so far, based on symmetry and expenditure in terms of lattice parameters. And essentially what we are doing, we are taking the 32 point groups and putting them into 7 boxes, the 7 crystal systems. And we have already noted that, for instance, the cubic crystals can have a lower symmetry than the lattices they are built on. For instance, we note that some of the cubic crystals may not have a pure 4-fold axis. For instance, the diamond cubic crystal is written with a space group F 4x1D 3 bar 2x1. In other words, it's characterized by a 4-1 screw axis. And if you're just looking at the point group symmetry, we can also think of it as having a 4 bar kind of an axis. So we will now try to classify the 7 crystal system based on symmetry and also based on the expenditure of the lattice parameters. First, based on symmetry, we already seen the lowest symmetry one is the triclinic crystal and the highest symmetry one is the cubic crystal. Now, the way this ordering is done is that we locate the order of the point group. In other words, if you take a cubic crystal, then we try to see that the hodohedral cubic crystal has how many independent symmetry operations, right? So, in other words, if I start with a single point, after the point group has operated, I would like to locate all the equivalent points which is the point group has generated. So, in the case of a cubic crystal, 48 such points would be generated, and therefore it has got the highest symmetry. This tree, apart from listing these various crystal systems in terms of an increasing order of symmetry, also sort of by these arrow marks points out to the subgroups. A subgroup is a concept wherein we try to understand if the symmetries are contained with another symmetry. For instance, we already noted, if you take a simple example of a 6-fold axis, then we know a 3-fold or a 2-fold axis is contained within the 6-fold axis. Similarly, let's go down and maybe pick up, let me take a slide here. For instance, suppose I take a cubic crystal 4x m 3 bar 2x m, we see that the 2-3 symmetry is contained within this 4x m 3 bar 2x m. In other words, it's a subgroup of the crystal. So, how do we rank these in terms of the order of the point group and order of the operators which lead to the point group? The cubic is the highest, which has an order 48. The hexagonal has an order 24, but we have to note that the hexagonal is characterized by a 6-fold, the cubic is characterized by 2 3-folds, and they are not subgroups of each other. Then the tetragonal is characterized by 16 operations or order 16, trigonal order 12, orthorhombic order 8, monoclinic order 4, and triclinic order 2. The subgroup relation should be cubic. The orthorhombic is a subgroup of the tetragonal, which is a subgroup of the cubic. And if I track from the bottom, the triclinic is a subgroup of the monoclinic, which is a subgroup of the orthorhombic, which is a subgroup of the tetragonal, which is a subgroup of the cubic. So, I can have an unbroken chain of subgroups starting from the cubic and leading to the triclinic. I can use an alternate chain, alternate path to go to cubic. The triclinic is a subgroup of the monoclinic crystals. The monoclinic is a subgroup of the trigonal, and the trigonal is a subgroup of the cubic. Another way of going to the top or to the hexagonal crystal would be the third path. The triclinic is a subgroup of the monoclinic, which is a subgroup of the trigonal, which is a subgroup of the hexagonal crystals. So, we can clearly see from this diagram that some of the crystals have higher symmetry than the other crystals, and the way we rank those symmetries is based on the order of the point group. Okay. So, we have the lowest symmetry ones at the bottom and the highest symmetry ones at the top, and we can by this network identify the groups and subgroups, and this is an important concept, especially later on when we deal with properties and other kind of concepts which are related to crystals. Mr. Patel has a question.
Sir, I have one simple question. Actually, if I consider benzene ring planar structure, and there are just 6-fold axis and one is center of inversion. So, if we write the total symmetry groups, we obtain one group. Just you written here. So, suppose you describe all the structures, all the crystal structures. So, you can draw any one example and show how we can see the all points.
Okay. Very good question. So, there are two important issues which you have raised. One is the symmetry of the, for instance, an isolated entity like a benzene ring. So, the question Mr. Patel has got is that suppose I am dealing with a benzene ring, okay, and it is an isolated molecule, for instance, what the symmetry of that. Then of course, I could have a crystal based on that molecule. Now, these are two independent things we already seen. For instance, you could have a very high symmetry molecule, okay, or a low symmetry molecule, but then when you make a crystal out of that, then this is an independent concept altogether, right. We have seen that, for instance, you could even have a cubic lattice, but then if you place a low symmetry molecule in it and that performs the role of a motif, then you could have a lower symmetry crystal. Now, this very concept you were mentioning, we actually discussed in detail in the chapter on symmetry, but here we are talking about order of the point group. So, we are not talking about the independent entities which go on to make the crystal system, and we are taking the highest point group of the holohedral class, okay. That is what we are considering here. We already seen within a cubic class itself there are many lower symmetry crystals also which have a lower order, right. So, we are considering the highest order one in making this classification. So, that point has to be absolutely clear. Regarding individual benzene rings, at this point of time I would not mix myself with this concept. Ultimately, I will have a crystal, I will find out, I will assume for now that that crystal has got the highest point group, and I am trying to then classify those in an increasing order of symmetry. But these individual molecules and understanding that symmetry of those molecules is a task which we took up in the chapter on symmetry. So, that is an independent task, and that would not bother us now, because you could start with, for instance, an hexagonal benzene ring and land up with a crystal. I do not know what crystal structures benzene would form, but it could form a crystal structure which is lower in symmetry than the hexagonal symmetry which it, for instance, could have, for instance.
So, that will totally depend on how we pack that molecule.
Yeah, absolutely. So, how we pack the molecules, and for now I will try to take those molecules which will give me the crystal of the highest symmetry, okay, because if we are writing a point order of the operation as 48, that means that I am using the holohedral class, okay, for this classification. This is a task now. The previous one was a purely symmetry based argument. Now, this is purely an expenditure on the lattice parameters. So, this is in some sense a lesser important task, but just for a what you might call an understanding of the unit cells and the preferred lattice parameters for those unit cells, we want to understand how they rank in terms of the, and we had done this exercise for the two dimensional crystals, and we had seen that we had defined a parameter known as terseness, which is nothing but the number of, for instance, let me do a calculation. For the cubic case, there are 6 parameters P, and there are 4 equal to among them. Therefore, my number of the terseness value, the P prime is P minus C, which is 6 minus 4, which is 2, and the terseness, we have 5 constraints. Therefore, my terseness would be 6 minus 5, which is equal to 1. That means, if my expenditure on independent parameters is less, then higher is that kind of an unit cell in this hierarchy. So, let me consider classify them, and let us start with the cubic case, and we saw that we have 5 constraints, 1, 2, 3, 4, 5 equations, and therefore, this is 5, and therefore, we got a terseness value of 1. For the tetragonal, one of these parameters is not equal to, and therefore, we have 4 constraints and my terseness value is 2. So is it for the hexagonal class, wherein now all the angles are constrained as before, but now one of the angles is different, and we have a number of constraints is 4, the terseness value is 2, and similarly for the trigonal the terseness value is 2. There are 2 constraints, and the triclinic has no constraints on the lattice parameters, therefore the terseness value is 6. Now, what this table does for you is that when we looked at the previous table, we saw that there is a cubic, tetragonal, orthorhombic, monoclinic, triclinic hierarchy, and that was based on symmetry. Now, based on our choice of unit cell, we have a different hierarchy here. From the cubic, we can have the lower level, which is the next level, which is the tetragonal, hexagonal, and the trigonal. The next level would be orthorhombic, then the monoclinic, then the triclinic. As you go down this tree, you will find that the terseness value, that means we are spending more on lattice parameters, which is in some sense a reflection of the fact that we are now considering unit cells of lower symmetry, and this is not the unit symmetry of the crystal, but the unit cell, and therefore we have to spend more on the lattice parameters, and therefore the terseness value goes up and this goes down in the chain. So, this is just a way of writing down the 7 crystal systems and the preferred unit cells. Okay. We have already seen this, and now let us write down the full table indicating the 7 crystal systems, the characteristic symmetry, the point groups within the crystal system, and the comments regarding these kind of a symmetry. And we had already seen, for instance, that the hexagonal crystals, for instance, is characterized by one 6-fold rotation axis, and this is written in a way so that 6 is in the first place. So we had made this, so now we understand the complete picture of the crystal system, the characterizing symmetry, all the point groups which are contained within the crystal system, and how to identify them based on a simple rule of thumb. For instance, suppose I want to identify a trigonal crystal, I would try to look out for a 3 or a 3 bar in the first place. So if I see or a 3 or a 3 bar in the first place in a point group, then I can clearly see this is a trigonal crystal. And an important comment we had made while discussing triclinic crystals is that the triclinic crystals could have a 1 bar symmetry, which means it can have a center of inversion. Of course, triclinic crystals could also have no symmetry, which is otherwise written as an 1-fold symmetry. So this is an important summary of all the 7 crystal systems and their point groups, and once and for all we have clearly said that crystal systems are based on symmetry and not on the geometry of the unit cell. So this point has to be absolutely clear. I will leave this slide a little bit for you so that you can see this and absorb all the information in this slide and try to sort of use it in a useful way whenever you see a point group of any crystal. And the important words to be noted are the words only wherever they appear. So you see that we have used the word only in many contexts, and that have to be noted. So it is time to summarize the salient features we have learned so far. So they are as follows as listed in this. A crystal is a lattice plus motif. There are 14 Bravais lattices in 3D which are based on translation. A motif is any entity which is positioned identically with respect to every lattice point. We will have a few more questions to ask regarding motifs in one of the coming slides. There are 32 different ways in which symmetries can combine, and these lead us to the 32 point groups. These Bravais lattices are 7 different symmetries which correspond to the 7 crystal systems. Conventionally, there are 7 unit cells which are chosen for these 7 crystal systems. Real crystals, this is an important point and we will have a lot to say about this. Real crystals are defected in many ways so that some of the symmetries present in ideal crystal are disturbed, and this disturbance could be locally or globally. So in other words, real crystals could be very different from the ideal mathematical crystals we have just now constructed, and we will of course try to understand how they are different from the ideal crystals we have constructed. So just to highlight the important points, the 14 Bravais lattices, the 32 point groups, the 7 crystal systems, and of course we have not dealt in detail. There is another number which comes up, which is the 230 space groups. So let us check what you have learned so far, and I just read the slide for you. The definition of crystals is based on symmetry and not the geometry of the unit cell. Our choice of unit cell cannot alter the crystal system a crystal belongs to. Crystals based on a particular lattice can have a symmetry equal to that or lower than that of the lattice. When all symmetry including translation is lost, the construction, the entity we have made, is called amorphous. And a very important thing which we considered, any property of the crystal will have at least the symmetry equal to the symmetry of the crystal, or typically it could be even higher than the symmetry of the crystal. And when you are talking about symmetry, we are talking about the point group symmetry in this context, and this is this principle known as the Neumann's principle. So all the language of symmetries and language of crystallography can be directly correlated with the properties and especially symmetry of the properties. So let us now answer a few questions we have learned so far, and Akruti will help me with answering these questions. So let me ask the first question. What is a crystal?
Crystal equal to lattice plus motif. Crystal equal to a symmetric unit plus space group. An array of entities in space having at least translational symmetry.
What constitutes a motif?
A geometrical entity or a physical property or a combination of both can serve a motif.
How is the classification of crystals made into the 7 crystal systems?
The classification is purely based on symmetry. Example, if a crystal has only one 4-fold axis, then it would be classified as a tetragonal crystal. This classification is not based on geometry of the unit cell as commonly perceived. Of course, if one has a cubic crystal, then it will be referred to the cubic axis system.
What are the 14 Bravais lattices?
There are only 14 different ways in which points can be arranged in 3D space such that each point has identical surrounding.
What is the relationship between the 7 crystal systems and the 14 Bravais lattices?
Based on symmetry, the 14 Bravais lattices can be put into 7 boxes, the 7 crystal systems. Example, all lattices with 2, 4, 3-fold axes are put into the box labeled cubic.
What is the relationship between the symmetry of a crystal and the symmetry with respect to its properties?
The properties of a crystal can have a symmetry equal to that of the crystal or a symmetry higher than that of the crystal. Example, cubic crystal have a spherical symmetry with respect to refractive index.
So I will thank Akruti for helping me out with the answers. Next we consider another important question. Why do we need to consider such arbitrary motifs? For instance, we had already considered various kinds of geometrical shapes in which we had arranged, for instance, triangular and more complicated shapes, and even chosen some very arbitrary kinds of motifs when we describe what motifs are. So the question we are asking is that, aren't motifs always made of atomic entities? So we will try to understand this question by considering a crystal made out of, typically these are the ball bearing balls which go into a cycle, for instance. Now the question is that, is it true that normal crystal, it is true that normal crystal we consider in material science, for instance copper, sodium chloride, fullerene, etc., are made of atomic entities, but the definition has general application and utilities. And the experiment I am going to describe now is typically done in many MSc labs, MSc physics labs, and the experiment is as follows. A ball bearing crystal is constructed. Actually you take an array of ball bearing balls, okay. So they put them in array and make a 2-dimensional crystal out of it. Then you use a spacer typically made of some kind of foamed polystyrene or polyurethane foam, and then on top of that you make another array, 2-dimensional array of such balls. In other words, you construct a 3-dimensional crystal. Now the motif in this 3-dimensional crystal is a macroscopic entity. It is nothing but a ball bearing ball. So the crystal which I make would look as the picture shown here, and this is just a projection from the top. And in this case what I can do a diffraction experiment, and we know that, for instance, suppose if you look at the Bragg's diffraction experiment, you would send X-rays into a material, for instance a crystal of sodium chloride. Here instead of using X-rays I would use microwaves, and typically the wavelength of such microwaves would be 3 cm, which is of the same order as the spacing of the ball bearing balls. So my wavelength of the microwave is similar to the lattice parameter spacing, and this is an important requirement for diffraction to take place, right. Whenever we do back diffraction, for instance the wavelength of X-rays is very similar to the lattice parameter spacing of the atomic crystals, and which is, for instance, sodium chloride, from which Bragg did his original experiment. So this crystal is now made of metal balls and not of atomic entities, and I can use my Bragg's equation, which is n lambda equal to 2d sin theta, and I can attain various peaks at various positions, for instance at 19.47 degrees, 41.81 degrees and 90 degrees. In other words, now I can make a crystal made of balls, ball bearing balls, and I can actually do a diffraction experiment. In other words, I send a beam of monochromatic microwaves and get a diffracted beam at various angles. In other words, the laws of diffraction are identical to diffraction of X-rays from crystals with atomic entities. For instance, this diffraction experiment with X-rays I could do on sodium chloride, gold, silicon or diamond. In other words, the language of crystallography does not change, the laws of diffraction does not change if I go from atomic entity crystals to crystals of this scale, which are macroscopic crystals. Therefore, my language needs to be consistent across these length scales, and later we will consider, and I would like to point out, people have made colloidal crystals. In colloidal crystals, these are typically spheres, micron sized or submicron sized spheres, which go on to form a crystal. And these crystals, these spheres themselves could be amorphous, for instance, and silica spheres are typically used to make some of these colloidal crystals. Therefore, the entities which go on to make a crystal could be in diverse length scale. There could be of the order of angstroms, they could be order of microns, they could be order of centimeters, and we could perform experiments of diffraction either with X-rays, with light, or even microwaves, and my results would be identical as long as my geometry of the crystal is, and the scattering distances and the symmetry of the crystal is that which is I use my language of crystallography to describe. So this is an important example. We should note that I need not constrain myself in the definition of a crystal to only to atomic motifs, because the language is applicable to a broader class of crystals, as I pointed out, and there have been other examples wherein they have crystallized viruses. So virus, as you know, can part time be living organisms, but they can also be crystallized, and of course in that state they are not active, but you can perform a diffraction experiment from that and they would perform a role of a motif in that crystal. So these are examples, diverse examples, and you know, a single virus would consist of zillions of atomic entities. Another example for a different kind of a crystal would be you could actually etch, or you could actually what you might call affect a photoresist material with opaque and transparent region, which can act like an element in optoelectronics. Therefore, I can take a photoresist material and then make an impression, an optical impression, which can act, and therefore the motif in this case is nothing but a region which is opaque or transparent in a photoresist material, and I can make a 3-dimensional crystal if you like, or a 2-dimensional crystal with this photoresist material. An even more curious example is the one which I am showing below, and I was pointing out that of course we may take up more examples later in the course, that a physical property can also serve as a motif which can go on to decorate a lattice point. So experiments have been performed, and especially these kind of experiments were performed in the last 10 years, within the last 10 years, that is, wherein for instance I make a crystal, and this crystal is now made up of purely laser beams. That means these red lines you see are laser beams. So you have laser beams in 2 directions. So this is a 2-dimensional laser crystal, if you like to call it, and clearly if I make a square crystal out of, you can see that this laser crystal can be understood in our familiar language of crystallography by considering a square lattice and a motif in the shape of an L. Additionally, alternately, of course, I can choose an alternate motif which I will show on the board. So alternately, I could consider a motif which is in the form of a plus. So each lattice point can be decorated a motif which is this part of the lattice. So each lattice point I put this plus, which is nothing but intensity of light here. So in other words, this is a very curious experiment wherein people have actually made a lattice, or a crystal to be more precise, a crystal made out of laser beams, and actually have diffracted matter through it. So this is an inverse of what the common diffraction experiment which you might think of, wherein you actually have a crystal made of atomic entities and you would send an electromagnetic radiation to diffract from here, from that kind of an atomic entity. So this is the inverse of the problem. In this problem, what I am doing, I am making a crystal out of electromagnetic radiation, which is a laser crystal, and of course these red lines would indicate certain kind of a density in electromagnetic density, and I can actually diffract matter out of this kind of a crystal, and this is possible because you know matter can act according to de Broglie's equation like waves. So we can clearly see that there are crystals of diverse types, but for all these crystals we can use a common language of crystallography, and the physics of these kind of crystals, depending of course, suppose for instance in the physics we are talking about is the diffraction physics is exactly identical as long as the common criteria for diffraction is met, that is the wavelength is similar to the spacing in the lattice or the spacing in the crystal. So we can have these kind of curious experiments and these kind of curious kind of motifs which go on to decorate lattices. So in this lattice, for instance, there are no atomic entities, and this is purely described in terms of a physical property which is now the electromagnetic radiation density. So We could have diverse kind of crystals, but the language of crystallography remains the same, and the analysis in terms of that language also remains the same. And I had also pointed out that we could also have a case wherein a motif could be a combination of a geometrical entity and a physical property. For instance, iron atoms with a magnetic moment below the Curie temperature would have of course atomic positions. In addition, each atom would have a magnetization vector which would typically within a domain inside the material would be aligned. So now I can describe the crystal in terms of just of course the atomic positions, but additionally I could take into account these magnetic moments and I could describe these crystals. Of course, this is done with some additions to the normal language of crystallography, and we use something known as color symmetry, and we have to note that these, when we talk about the combination, the symmetry of the structure could be lowered, because if all the magnetic moments are aligned, then you would notice, for instance, even if I start with iron which is a BCC iron, the symmetry of the structure could be lowered if all the magnetization vectors are aligned. Okay. So this is a case wherein we need to consider a physical property and a geometrical entity. Yeah, Mr. Ravi has a question.
Sir, in the case of Fe, we have Fe atom as well as the magnetic moment below the Curie temperature. While classifying the crystal, we will consider both these properties simultaneously, or we can take either of these two and classify the crystal.
Very important question, actually, and question which we are actually very soon going to, on the coming slides, very next slide or one of the coming slides, going to answer this question. So Mr. Ravi's question is that when I am describing a ferromagnetic iron, a crystal of ferromagnetic iron, and I am sitting within a domain of this ferromagnetic iron. Now that region, would I describe purely based on the symmetry of the iron atoms, or should I take into account the magnetic moments? As we shall soon see, we could do both these. We could just ignore the magnetic moments, or we could take into account the magnetic moments. But I will go to the board to explain you some possibilities. Now let me consider an ideal two-dimensional crystal. Okay. Now assume that there are atomic entities sitting in these lattice positions. Clearly, the crystal I have constructed now has got 4 mm symmetry and it is a square crystal. But now suppose I want to take into account the fact that suppose all the atoms additionally have magnetic moments which are aligned. So in other words, I am sitting within a domain of the magnetized crystal. Now there are two possibilities. When all the spins or the magnetic moments get aligned, there is a possibility that it can actually change the lattice parameter. What was the original lattice parameter? A, and this included angle was 90 degrees, right? So my two lattice parameters are the same and the included angle is 90 degrees, therefore it was a square crystal. Clearly now, if I want to include the magnetic moments in my description of the crystal, this is no longer a square crystal, because now the only symmetry present in this crystal, the diagonal mirrors would be lost, the four-fold axis would be lost, and therefore I would have a mirror plane here. And this would have a lower symmetry and this would be a rectangle crystal. So this part we already know. But the important question I am asking, which is what is relevant to your question, is that can this magnetization moment itself change the lattice parameters, in addition to the fact that if I look at the symmetry, it is already, we know it is a rectangle crystal. It could so happen, because of the magnetization moment, there could be a selective change in the lattice parameters. For instance, either there could be a contraction, expansion along this direction, or one of those things can happen, because now the physical property is aligned, right? So there is no random and there is no averaging. And if that happens, even the lattice parameters would change, and in that case automatically my fourfold axis would be lost and it would be a crystal of lower symmetry. Even though I am not taking into account this magnetization vector in my description of the crystal, if the lattice parameter changes as a consequence of this kind of an alignment, then I can no longer call it the higher crystal, higher symmetry crystal, but it automatically symmetry has been lowered. Assuming that that kind of a distortion is very small and it can be ignored, then when I ignore the magnetization moment, I will call it a square crystal, and when I take into account the magnetization moments, I will call it a rectangle crystal. We had considered on our early stages of this lecture series an advanced definition of a crystal, which said a crystal is equal to a space group and an asymmetric unit. In the lattice plus motif definition, the lattice was performing the role of how the repetition should take place, and the motif is what the entity which was to be repeated at the lattice points. We had just said that this advanced definition based on a space group plus an asymmetric unit, which is typically the preferred in the language of crystallographers, is possible. Though we are not taking up this definition in detail in this course, I thought it would be worthwhile that at least we consider one example of how such a description is possible. Now, let us consider an array of arrow marks. Of course, these are decorated arrow marks with a certain kind of a triangle on top of the arrow marks. Now, and you can see that the arrow marks have been inverted from point to point. So, we had an array of points initially which had a spacing a by 2. The first point I put an arrow mark upwards, the second point downwards, and so forth. Now, I can describe such a crystal, which is now a one-dimensional crystal decorated with a two-dimensional motif. In other words, I made a relaxation with respect to the dimensionality of the motif, which we did repeatedly previously in various examples to clarify certain concepts, and now I want to understand it in the language of space group and asymmetric unit. Now, I can see that if I take this arrow mark, it is repeated at distance a. So, I could use this as my lattice translation vector, and I could use the typical motif to describe it, but I will not do that. I will use this more refined definition of a crystal, and in this case now my space group operator would be a glide reflection operator. G is used as a symbol for it sometimes, okay. And what does the glide reflection operator do? Suppose I have a repeat unit of A, the glide reflection operator moves the asymmetric unit by distance a by 2 and inverts it. It moves it by a by 2 and inverts it, moves it by a by 2 and inverts it. So, we have seen that this is the property of a glide reflection operator. In other words, suppose this is my pen, which is the arrow mark with a certain decoration, it would move by a by 2, which is half the lattice parameter, and invert it. It will move it by a by 2 and then invert it. It will move it by a by 2 and invert it, and I would get the entire crystal. So, now I am considering a symmetry operator, a glide reflection operator, and we have already seen the glide reflection operator has symmetry, translation symmetry built into this operator along with this property of reflection. So, in other words, the mirror plane for, which is not a true mirror plane but a glide reflection mirror plane, the horizontal plane can act like the mirror plane. So, the glide reflection operator is a more sophisticated operator, and it operates on this asymmetric unit, and asymmetric units are typically regions of space. So, the region of space is marked by this pink colored box, and it contains this entity which is part of the motif, okay, the original motif in the language of lattice plus motif. So, this pink region is taken, moved over by a by 2 and inverted, and therefore, whatever the contents of that unit are also moved and inverted. So, therefore, I can write down this whole crystal as this asymmetric unit, which extends from say for instance from here, which is from this is a by 2, this is a by 4. So, minus a by 4 to plus a by 4, and so this is my extent, and with a certain z extent or the other axis, and with the space group operator which is G. So, in one dimension my G operator combined with this asymmetric unit would give me a crystal. So, this is just a perhaps a very simple and introductory way of introducing the concept of a space group and asymmetric unit, but this language is the language which is typically found in the international tables of crystallography and other regions where they want to describe crystals. But for now, most of the concepts we are dealing with are in the language of lattice plus motif. So, let us return to the important question, the question which Mr. Ravi asked: how do we go from ideal crystal, an ideal mathematical crystal, and reach a real crystal. So, some things we may note, for instance, ideal crystals may have perfect positional or orientational order with respect to geometrical entities and physical properties. In defining real crystals, some of these strict requirements may be relaxed. So, we may relax some of these requirements, and we will do that in a form of a flow chart in the coming slide. So, we may only consider the symmetry or the order with respect to the geometrical entity, and we will also see later on that the positional order may be only in the average sense, and also the orientational order may be only in the average sense. In addition, we note of course that real crystals are finite and can have other kind of defects. So, let us go from ideal crystal, and in this case I have made a little further leap of or extension of the logic, wherein not only I am starting with an ideal crystal, I go up to an entire component. So, we know that all these entities, the motifs typically could be at the atomic scale. So, we could be typically talking about angstroms, and we are talking on the other hand a component which could be a macro scale component, which could be centimeters or meters in dimension. And we want to see how I can go from this ideal crystal to a component, and of course at this stage we will not consider all the concepts in detail, but we just want to outline a complete flow of logic so that we can understand tomorrow that if suppose I have a failure in my component, then what are the length scales I need to consider these. The length scales are clearly across various dimensions. So, you can have from angstroms, which is 10 power minus 10 meters, to meters. So, you may have to travel 10 orders of magnitude in terms of the dimensional space in order to understand why the component had failed. So, there could be reasons at the component level, like for instance the component could have a sharp corner which could lead to a stress concentration. It could be at a lower scale, it could be a scale which we call, as we will see later, what we will call the microstructure, or it could be at an even lower scale, and we need to consider all these scales when we want to track down the problem. So, let us see how we can go from an ideal crystal to a real crystal to something known as microstructures. Of course, microstructures will be dealt with lot of detail in the later part of the course. Then to a material, which is what commonly we deal with. For instance, I have got here a material with me, which is of course not a single material, it is a combination of wood and a certain kind of fiber which is used for duster. It could be material like a chalk, for instance. It could be any kind of material, and some of these examples I am showing here are not crystalline, but here since we are doing mostly a description of crystals, and so we will consider examples as if we are starting with real crystals. So, let me start this long journey with an ideal crystal, and I will do this in two slides, this slide and the next slide both, so that this concept sink in slowly, and some of the terminology additionally we are introducing here also sinks in. But as I pointed out that some of this will only become clear much later in the course, some of the terminology will be understood in detail only later. So, we have an ideal crystal. Now, what I can do, I can only consider the geometrical entity or the physical property like we did in the case of the magnetization vector. So, I could do that, and I could have a reduced definition of a crystal. That means now the crystal is not, it's either considered in terms of the physical property or the geometrical entity. I do not want to consider both. Further, I could even reduce the definition even further by considering only the orientational or the positional order. Now, for instance, I could have a system which has both kinds of an order, an orientational order and a positional order, and I want to consider only one of the two in describing my crystal. At this stage, of course, it may be difficult for you to understand all the implications of the statement, and we will take up examples later on to understand what I mean by only orientational order or positional order. A simple example, I will take a one dimensional example to show you on the board what I mean by this statement, but more examples will come up later. So, let me take a one dimensional crystal here which I have drawn on the board, wherein I have a system which is perfectly orientationally and positionally ordered. That means this distance is perfectly A as I go from each atom to the next atom, right. Now, I could do something that now, so this system can be disordered with respect to the orientation, for instance, and I go from one arrow to the next arrow. So, even though the spacing between the atoms is A, the orientational order is not maintained, and therefore I could have a reduced definition of a crystal in which I consider only the positional order. The other possibility would be that there is positional disorder, but there is orientational order. In other words, suppose these were my original lattice points which are A spaced. I could put my atoms, of course I can do it in 1 dimensions or 2 dimensions in various places with respect to the lattice point, but I put all my arrows upward direction. So, such a system is orientationally ordered but not positionally ordered. Such a system on the top is positionally ordered but not orientationally ordered, and I can use a reduced definition of a crystal in which I consider only one of these kind of orders, and we will see better examples later on. Therefore, I could reduce my definition first by considering only the geometrical entity or the physical property, and further reduce the definition based on orientational or positional order. Then I can go from still what you might call a reduced definition of a crystal to a real crystal, wherein I introduced crystalline defects, and we will have entire chapters devoted to crystalline defects. And we also need to note that we always have a finite crystal, we never have an infinite crystal in reality, therefore we have to introduce free surface. And the third thing, which is thermal vibration. And if I take a snapshot of a crystal at any point of time, the picture could look like the one I have shown here. That means atoms are vibrating about their mean positions, but they are displaced with respect to their atomic positions, which I consider the seat of the lattice point. Okay. Now, therefore, there are unavoidable defects in materials like crystalline defects, free surface and thermal vibration, and therefore I could have a real crystal which has these kind of defects. Then it is not necessary that my entire material is made up of a single kind of a crystal. I can put multiple crystals which I call multiple phases, and therefore when I put in multiple crystals, I not only have a free surface but also have an interface between the two materials. For instance, suppose I want to make a crystal which I can, for instance, this were my, suppose for now assume that these are crystalline materials, then I would have an interface between these two kinds of a crystal. So this is something which will become unavoidable when you put in multiple phases, and this would give rise to a concept of a micro constituent. So these concepts we will take up later in the course, wherein we will see names like, for instance, pearlite. Pearlite is a micro constituent which is made up of alpha and Fe3C, which is typically found in plain carbon steel. So you can see those kind of micro constituents, and they are made up of multiple phases with interface, and interface itself is a defect. Then I can put in multiple micro constituents, and additionally I can add residual stresses. Typically, as you will see later, that residual stresses are unavoidable in material, and there are multiple sources of residual stresses which we will also see. So I can take in micro constituents and add residual stresses, and I can get something known as a microstructure. Now this is a new way of defining microstructure. This is not the classical definition found in many places, wherein a microstructure is defined as a structure seen at high magnification. So this is a new way of looking at microstructure, but this is a functional way of looking at microstructure, wherein you have micro constituents and residual stress added in. We will also define this microstructure in a slightly different way, different way compared to this flow diagram in one of the coming slides. But starting with microstructure, I can put in many microstructures to make a material. So material, typically what you might consider a block of material, may actually consists of many microstructures. Of course, you could also have a single microstructure, which would be a trivial or a simple example of a many microstructure case. And finally, I can put in many materials to make a component. So a single component, for instance, which you practically see in everyday life, could have many kind of materials, and often these materials all need not even be crystalline. For instance, a single component could have a plastic region, a region which is metallic, a region which is ceramic, and so forth. So therefore, all these kind of materials can go together to make a component which is obviously performing some function, and this component itself could be a part of a larger machinery, and therefore that is the next scale you need to talk about, a single component going on to make a larger machinery which is performing some useful function. So I can start with an ideal crystal, and going through this flow chart by relaxing certain considerations and introducing certain new definitions, I can go to a component, and not only am I going down in terms of certain kind of what you might call an ideal mathematical description, but also I am going across length scales. So, this additional point has to be noted. So, let us look at the same slide, because there are so many new concepts involved, in a slightly different way as shown in the next slide, and I thank Professor Kantesh Balani for making this slide for me. So, you have ideal crystals, real crystals, microstructures, materials and components. So, this is an alternate way of representing the same thing, and so we can have an ideal crystal which considers both geometrical entity and the physical property. I can have a reduced definition of a crystal which I call a crystal star, wherein I consider either the geometrical entity or the physical property. Further, I could have an even more reduced definition of a crystal, wherein either I consider the orientational order or the positional order. Further, I could introduce various kinds of defects, and we will consider these defects in detail later, which are known as crystalline defects. I can introduce a free surface, which is absolutely unavoidable for any real crystal, and finally thermal vibration, which is also unavoidable in real circumstances. Then I can use this real crystal to actually construct what is known as a micro constituent, wherein multiple crystals are put together and which will have an interface which itself is a defect in the overall structure. Finally, using these micro constituents, I can construct a microstructure wherein a multiple micro constituents, and additionally I can put in some amount of residual stress, and as we said, this kind of a definition of microstructure is based on functionality, because this residual stress could have important implications in terms of the properties of the material. Ultimately, what I want to do in a real material is to have a microstructure property correlation, or what we call more commonly the structure property correlation. And I want to understand this structure property correlation. Obviously, I need to understand all the length scales below it, which means I need to understand the crystal, I need to understand the defects present in the crystal, and additionally this is residual stress, and therefore this residual stress has been put into the definition of a microstructure. Therefore, the next stage would be to understand this microstructure property correlation, which is an important goal of material science. Now, when of course I am looking at a component and the performance of a component, especially in a bigger machinery where this component goes, I need to also look at the various aspects regarding the mechanics of the component, the design of the component. Typically, this is not under the basic purview of material science, though we would also like to consider that. But as I said, microstructure itself gives an important handle onto the properties, and therefore I need to have a definition of a microstructure and the understanding of the microstructure, which of course starts from various length scales, and the first starting point would be an ideal crystal. So, I have a material in which there are many microstructures, and finally I have a component which could be a combination of many materials. And if you look at any working component in a modern machinery, you would note that it is made up of many materials. If you even take a normal camera for instance, you would note that, or a laptop, or any one of these components, or any one of these devices which has components in it, you would note that many materials go on to make such a device, and it is very important for us to understand not only the individual constituents, but the assembly which finally leads us to this grand component and this grand machinery and the device. So, we have seen that an important term which we have newly introduced in this whole structure is the microstructure, and this term is very important from a material science perspective. And for instance, in this course on structure of materials, this is an important length scale, and if I understand my microstructure, then quite a bit of my properties can be understood based on this microstructure. And I am defining my microstructure slightly differently here, which includes all my length scales. So, what is the way I am defining my microstructure here? It is phases in the distribution. So, I have multiple phases, and typically each one of these phases could be crystalline or amorphous, or could be other kind of phases, and I add defects to this distribution of phases, and these defects could be various kinds of crystalline defects like dislocations, twins, stacking faults. There could be larger defects which are bigger in size, for instance voids or cracks, and some of these cracks could be big enough to be even seen with the naked eye. So, I put in all these defects into this distribution of phases, and finally add my residual stress, which would give me a definition of a microstructure. Now, the important point I need to consider is what do I mean when I mean phases and their distribution? Of course, we will have a lot to say about the defect structure in a material, and at this point I would like to describe a little more about the very first thing in this, the phases and their distribution, and also something about the origin of this residual stress. Okay. And this origin of residual stress, again, like our journey into a component, would involve multiple length scales. So let me start with the origin of residual stress. The origin of residual stress could be from very small length scale of the angstrom length scales. For instance, defects in crystalline materials. They could be vacancies. We will of course consider what these in detail later, but they could be defects in the crystal. For instance, a vacancy is a missing atom in, for instance, a copper crystal. There could be more complicated defects, line defects like dislocations, whose extent of influence exceeds beyond an atomic diameter. There could be microstructural origin of residual stress. For instance, phase transformations or voids and cracks could lead to residual stress. And of course, I am using iteratively the word microstructural within microstructure, but the way these definitions are voids and cracks, we understand what is the origin of these kind of residual stresses. And finally, I could have thermal residual stresses, which are typically across the whole component. And often you would notice that thermal residual stresses can be used in a very beneficial way. For instance, we can introduce surface compressive stresses which can toughen glass. So therefore, it is not necessary that residual stress always is bad. It could be deleterious or it could be beneficial based on the situation. But residual stress is very, very important, and the behavior of the material is quite a bit governed by the presence of this residual stress, and this is the reason that it has been included in the very definition of a microstructure in this course. Now look at phases and the distribution. The word distribution hides within it quite a bit of detail. It may not be possible at this stage to go into all the details, but let us take a small sampling of what we mean by phases and the distribution. For instance, what we could be talking about is a size, and not only a material may not have a single size. For instance, suppose I am talking about a second phase, a second kind of a crystal in a matrix, then it may not be necessary that the second phase has a single size as shown here, and it could have a distribution in sizes. But I need to know the sizes and the size of all the particles which are present, and more important, a statistical analysis of all these sizes, which I call a size distribution. The second thing I need to know when I am talking about phases and their distribution is the volume fraction. In other words, if it could be that these black phases with respect to the white matrix could be 10% in volume fraction, 20% in volume fraction or more, and this would make a difference to my properties. Therefore, when I am talking about phase and the distribution, I need to know the volume fraction, or equivalently I may also want to know the weight fraction. Third thing, I need to know the morphology of the phases. For instance, suppose the second phase here is my black phase. It could be spherical or circular into two-dimensional cross section, or it could be in the shape of needles as shown here, and this again would make a lot of difference to my properties. So is it circular or is it this needle shape would make a difference to my properties. And finally, how these phases are distributed is also an important thing. For instance, here the size of the second phase is larger with respect to this, and assuming that the volume fraction is identical, then these two distributions would have different properties when I am considering, for instance, a mechanical behavior or any one of those kind of aspects which would depend on my microstructure. Now, this kind of a microstructure perhaps has the same volume fraction of these black phase, but now the distribution has changed, and this would again affect my properties. For instance, you can additionally see that these needle shaped things have a sharp corner, and this sharp corner could be a place where cracks could initiate, and therefore my properties would change if I not only change my volume fraction, change my size and its distribution, change the morphology of the prostate. As you can see, the morphology has changed. That means the shape of the prostate has changed from here to here, and all these things put together would go on to describe a simple kind of a phrase I use, which is phases and their distribution. So let me try to once again emphasize the important alternate way of defining a microstructure, which is perhaps more functional than the standard definition. In the standard definition, we always define a microstructure as the structure seen at high magnifications, typically optical micro magnifications, but of course you could also have microstructures which are seen at in a transmission electron microscope, wherein you are looking at nanostructures. But ignoring the scale aspect here and more emphasizing on the functional aspect, we can call a microstructure as phases and their distribution, the defect structures within, and these defects could be defects within a single phase or between phases, or could be more macroscopic like voids and cracks. And finally, we have to include residual stress if we want to understand the important thing which is known as the microstructure property correlation. And to emphasize this important aspect, that whenever I am talking about an ideal crystal versus a real crystal, there are defects which are totally unavoidable. However ideally or however nicely I like to prepare my material, try to make it a single phase material, and these three defects which always arise are thermal vibration, surface and vacancies. And this origin of vacancies we had briefly touched upon when we did try to understand what are the thermodynamic quantities at the beginning of this course. So vacancies can be equilibrium thermodynamic vacancies, and therefore they always arise at positive Kelvin temperatures, and these three defects always will be present in a crystal. Therefore, my crystal can never be an ideal mathematical crystal, and I will have to work always with one of the reduced definitions of a crystal, and more typically I would like, starting from a ideal crystal, go down to a more functional definition of microstructure, and finally the component, wherein I am now talking about a performance of a component. So I have an ideal crystal, properties of a microstructure, and finally a performance of a component. So this is our goal, and at least till the microstructure we will take it up in this course on structure of materials.